Waves, fantastic. Thank you, everybody. So hello, good morning. My name is Matt Wood. I'm the General Manager of Data Science at Amazon Web Services, which is a rather bizarre title, but basically means that I get to talk to smart people such as yourselves about the role that cloud computing is playing in virtually all industries. So my specific focus is on high-performance computing and big data and connected devices, but I'll also talk to you a little bit today about some of the usage that we're seeing beyond those areas. So just to give you a bit of background, some of you may know a website called Amazon.com. Who here has an account for Amazon.com? Everybody, good. Well, the good news is you're good to go on AWS. But a lot of people ask me, what is a company best known for selling books and trampolines and table saws and all the rest of it, operating a very, very large global system of cloud computing? And the truth is that about 15 years internally at Amazon, we started to recognize that we had a lot of internal expertise that we could expose as services, literally through APIs. And we started doing this with catalog data. We started opening up ISBN and album art and author details and all these sort of things. And what we saw was a tremendous amount of innovation. Customers were able to take this information from our own catalog and build out very inventive things for their own products and for the benefit of their own customers. And so we moved from just being a retail organization to having a kind of second leg on our chair in something we call merch, which is merchant services. So offering some of our expertise in fulfillment and managing that data to customers to build into their own products. And about 10 years ago, I guess we had a blinding flash of the obvious. What would happen if we were able to take that same services API approach and not just apply it to our fulfillment and our operations, but apply it to our expertise in managing data centers? And that's where AWS came from. So this isn't excess capacity left over from Christmas or anything like that. This is a completely separate part of the business. And in fact, today, Amazon Retail is just another customer to us. Where actually AWS itself is in a physically separate building, and Amazon Retail is another customer. They run on exactly the same services, on exactly the same platform as all of our other customers. And now every web request that you hit that goes to Amazon.com and .co.uk and .de goes through the Amazon Web Services platform. We got started about 8 years ago. We launched our first service, Amazon S3, the simple storage service, on the 14th of March in 2006. And we've been steadily building out our platform, focusing initially on what we considered the primitives for cloud computing: storage, compute, networking, databases. You can see we launched EC2, the Elastic Compute Cloud, a couple of months after S3. A couple of years later, we launched the relational database service. And we've continued kind of this pace of innovation of adding DynamoDB, a NoSQL database, Redshift, a columnar data warehouse, which we launched last year. And over time, you can see that this sort of pace of innovation is steadily increasing. So way back in 2008, we added, 29 new services or new features to the platform. Last year, we did 280. So we're continually picking up the pace. This year, we've already done more than 180 launches on the platform. So these are major new features and significant services added to the platform that you can take advantage of straight away. So I think we're on target to maybe even beat last year's stellar year. So what I wanted to do was basically talk about some field notes, some observations that I've had. I've been at Amazon just over 5 years. I was employee number 3 over in Europe for AWS. And just basically talk about some of the patterns and some of the trends that I've seen from customers actually using this platform. It's been in operation now for 8 years, and I think we've collected a lot of information about how customers are really using this stuff, what the business drivers are, and the value that they're getting out of it. So one of the trends that we've definitely seen is an increase in the amount of data which is available to customers. So we end up with customers that have lots and lots of data. But that's really just the start. What happens when you have lots and lots of data is you start finding lots and lots of uses for that data. It's kind of addictive once you start analyzing data, once you start working with it. And the more productive you are, the more benefit you get out of it, the more new ways you find in working with that data. And typically, if you have lots of data and lots of uses for that data, you have a lot of people inside your organization that want to take advantage of those uses. They want to take advantage of that data. They want to start knocking down the walls between the silos. And increasingly, that happens across lots and lots of different locations. So you have lots of data, lots of uses, lots of users, and you want to do that over as distributed a surface area as possible. Now, there's a lot of value in doing it this way. Now, but the challenge is that all of these things are effectively multipliers for complexity. So they're multipliers that if you get it wrong, this can become a very, very complex environment to work in. But what I want to talk about today is how the cloud and how AWS and how its customers, most importantly, are able to remove this complexity for their own users and remove this complexity for their own business. And talk a little bit about where they came from and what we went through. So it's just a bunch of stories, really, no big deal. So the first thing I wanted to talk about was solar panels. Who here thought they'd talk about solar panels today? Good, no one. A customer of ours at University of California asked a very, very simple question. Can we make a better solar panel? Now, the truth is that solar panels, photovoltaic cells, have traditionally used kind of physical chemistry as the basis. But there's a lot of innovation happening in organic chemistry today. And so what happens is you can basically synthesize a molecule. You need to be able to purify it to put it into a photovoltaic cell. Then you need to analyze how well it's doing. And eventually you get to decide whether you're going to go and make a solar cell out of it. Now, in order to do this, you need a lot of equipment. You need to be able to identify the organic compounds. There's literally millions of them. And you need, typically, this is the way this is done today, another low-cost elastic resource, grad students. So what you tend to do is you use this sort of synthesize, purify model. You analyze whether this thing works, and you get to decide if you put that into production. The challenge is that the conformational space is absolutely vast, and finding molecules which you think are going to work is incredibly expensive. This process can take hundreds of thousands of dollars to get right, and you don't know until the end whether the thing is going to work and actually work in a photocell. So we had a customer who wanted to sample 205,000 of these molecules. They wanted to basically take virtual molecules and figure out whether they were going to work or not, whether they were going to produce an effective photocell at the end of it. And this is a relatively complex environment. It's a quantum mechanical simulation, so it uses molecular mechanics and quantum mechanics in order to identify whether these molecules are going to make good photocells or not. And the way they went ahead and did that was with a customer of ours called Cycle Computing. These guys they're actually based over here on the East Coast. And this is a picture of their dashboard as they were running an enormous multi-region supercomputer up on AWS. Now, the horrid, bitter truth about supercomputing is supercomputers are usually too small when you need them, and they're too big all the rest of the time. So when you have to fix them and cool them and all the rest of it, they're always too big. But actually, when you want to run a simulation like this, as one as complex as this, they're never as big as you need them. Apart from when your data center walls can move like they can up on AWS. So you can see here we're running hundreds of thousands of cores across 8 different geographic regions. And Cycle Computing built a specific scheduler to allow this to happen. So it handles all of the distribution of the work. It forms mini, tightly coupled clusters across these different regions using these very high-performance environments and the high-performance networking we have under the hood on EC2. You can see all the instances there, and this graph shows the provisioning time. So you can see that in a couple of hours, what's that, from 1600 to 1900, so just in 3 hours, they had about 1.21 petaflops of compute capacity up and running across 16,788 instances running globally. This is the sort of thing that you can do when you have a very large global platform and you are able to distribute your work across the regions within that platform. What they ran in the 18 hours that this cluster was working for was 264 years of wall clock compute time to process those 205,000 molecules. And they ran the whole thing in just 18 hours using these 16,000 instances. Now, all of that is dramatic and impressive enough, except the really impressive thing, I think, is the cost. So this came in at just $33,000. That's about the price that you would pay for 1/3, just one step of that initial pipeline of synthesizing it. But they were able to do all of these virtual instances in about 18 hours. Now, I think what's interesting is, under the hood, how were we able at AWS to enable this? What features did they use? What sort of technology did they employ? And the truth is, it was relatively straightforward. The truth is that when you have a range of cost models for customers to take advantage of, kind of wonderful things can happen. Wonderful things like a $30,000 petaflop supercomputer. And the way that we look at things is we have a lot of data centers, and we have a lot of servers inside those data centers. And one of the ways that we drive economies of scale on the AWS platform is to ensure that those servers are as utilized as possible. So we want the utilization to be as close to this dotted line as we can possibly get. And we have a number of different pricing mechanisms to help us get there. So first of all, we allow customers to reserve capacity. They pay a small upfront fee, and they're guaranteed to have that capacity, and that fills up a certain amount of our utilization. Then we have customers using on-demand capacity. They can spin up and spin down whatever they need to. But you can see here that there's still a gap between the on-demand plus the reserved and the utilization that we need to get to. So what we allow customers to do is bid on that capacity. They can name their own price for the compute that they want to use. So if you want to run a 1.2 petaflop cluster, you can bid against that underutilized capacity and spin it up at a dramatically lower cost. And this is available to everybody. Anybody can take advantage of this. But it's one of the things that we do under the hood to enable these very, very large-scale supercomputers to spin up. So let's talk about video games. A customer of ours representing a large big box technology store, Razorfish, they wanted to answer an even simpler question, not forming new photo cells. They just wanted to know who buys video games. Very, very simple, straightforward question. Or so you might think. The way they went about answering this was pretty interesting. They used a Hadoop cluster, spun up on AWS using a service called Elastic MapReduce, which manages all the internal workings. They loaded in 3.5 billion records, 13 terabytes of clickstream logs, and 71 million unique cookies every single day. And they loaded that into Hadoop. Again, this is the sort of thing where they didn't really know what sort of data they had available, and they didn't know how they were going to navigate that data. And what Elastic MapReduce and Hadoop allowed them to do was to basically discover and navigate and explore that data in a way that wasn't otherwise possible because they just didn't have the capacity. And they answered, they found their answer. It seems pretty obvious when you think about it, but people who buy video games buy really huge TVs to play their video games on. So you can look at this data, and they didn't know this before. And what they did was they used this to retarget, to place their adverts and to do better customer segmentation. And they could get to the point where they could go kind of a step deeper. And it turns out that people don't just buy huge TVs. People who buy huge TVs buy more sports video games. And so they could use this to really segment their customers, place the right ads next to the right products on their website. This creates actually a better customer experience because they're seeing more relevant ads and obviously increases the click-through on those ads. And they saw a 500% return on ad spend. Now, this is value. This is money that's just being left on the table. All those logs probably just got rotated off those servers before they started working in this. They certainly weren't coalesced and explored in the way that Hadoop allows you to do. And as a nice benefit, they saw a 17,000 decrease in procurement time of their servers, which seems pretty obvious because you can do it in about 30 seconds on AWS. So whilst we're talking about advertising, let's just take a quick note. Ad segmentation and delivering the right ad is one thing. Dynamic retargeting is probably the new hotness in ad tech at the moment. And a customer of ours called AdRoll wanted to answer another question. How do we serve the best possible ad? What is the best possible ad to show a particular user at a particular point in time? And if you're not familiar with ad tech, this is basically how it works. If I'm a customer browsing a website, I go up and I hit a bunch of ad servers, and they tell me which ad to download and display in my browser. Very, very simple. Except the problem is actually relatively complex. It depends what's on the page, depends the current bidding conditions of the different companies that want to place ads. It's a relatively dynamic, or it's a very, very dynamic environment, and picking the best possible one is very, very challenging. So behind those ad servers is typically a very, very large bidding engine. This is a fleet of servers which are continually evaluating the current environment, the bidding environments for people that want to place ads. And underneath that, AdRoll used DynamoDB. So DynamoDB is a NoSQL database store. So what's interesting is the scale at which this operates. So they have about 10,000 advertisers running inside the system at any one time. Customers are using this across 100 different countries, and they have about 1.5 petabytes of advertising assets just in S3. This is just this one customer. The biggest challenge for these guys is they have an absolute hard limit on delivering those ads of 100 milliseconds. So all of that evaluation, all of the understanding, all of the bids, tendering, all of that work has to happen in less than 100 milliseconds so they can get the ad back to the customer so they can view it before they go off to a different page. They never want to interrupt the browsing experience of the customer. So this 100 millisecond delay is very, very challenging. The reason that these guys like using a service like DynamoDB is that DynamoDB has a very, very stable provision throughput model. So it is able to continually deliver the same level of throughput, that is reads and writes, that you want from your data store, irrespective of the amount of data that it's handling and irrespective of the flow of traffic to the data store. So it's able to deliver this very, very complex evaluation in very, very short time. And DynamoDB has a single-digit millisecond latency expectation. And what I wanted to do was because these ad roll company deliver customers in all these different countries, it's not enough just to have one DynamoDB instance. The latency of the network going round, let's say if the customer is in Australia, going back to America, the latency would significantly impact that 100 millisecond hard boundary. So what these guys do is they continually replicate that environment across the globe, so across 4 different regions on AWS. This is something with a very small ops team, that a very small company with a lot of customers and a lot of growth. They grew 15,000% in their second year of operation. So very, very fast growth, and they're able to distribute on a global level their environment and have it operate in that 100 millisecond time frame. So they're able to synchronize hundreds of millions of records in sync. And they manage about tens of thousands of writes per second using Apache Storm to keep all of this in synchrony. And on the back end, DynamoDB is just churning through whatever it can in order to keep this system flowing. So I looked at all of the data for DynamoDB. This is in a single region, and plotted the average latency. So you can see there the average latency for requests to DynamoDB remains very, very stable throughout this week of operation. Particularly when you see the number of requests rising again and then again and again, day over day over day. So DynamoDB provides a very, very, very stable environment to run ad tech workloads. It's also very popular in gaming. The question is, how do you build a system like this? DynamoDB is a miraculous system in that its API is tiny. You can fit it on a single slide. It only has a couple of levers to control the throughput, and that's pretty much it. It's very, very simple, and it's extremely high performance, even at this very large level of requests. And we spent a lot of time designing DynamoDB. It evolved out of actually an internal system that we had running on Amazon.com, and it's now used by tens of thousands of customers across the world. And a friend of mine back at headquarters in Seattle has a great phrase for how he thinks about designing a system. He's the chief architect for DynamoDB. How he thinks about designing a system like this. He says, the Lord of large numbers is your friend until you reach those very, very large numbers. So the law of large numbers says that the more times you do an experiment, the average of that experiment is the true value. And that's true except for when you get to enormous scale and the sort of scale that we handle with DynamoDB. At that point, we have a very formal mechanism for defining the feature set and defining for how DynamoDB operates. So we have a very precise description. We use a programming language, I guess, called TLA+, which allows us to formally assess the product description of DynamoDB. This means that we don't just have a relatively loosey-goosey definition document. We have a very formal specification which we can evaluate against, and we can test and test and test against that at every scale, and we can simulate all the different edge cases that start to happen when you get to the sort of numbers that DynamoDB deals with in order to deliver what our promise is to customers, which is very, very low latency. So let's talk about social gaming, somewhat related. Nintendo asked a very simple question. Can physical and virtual worlds interact? This is an interesting question. Nintendo obviously make gaming consoles, and they make a whole bunch of great games. They also make the popular 3DS handheld device. And they wanted to bring the social experience of customers just walking around, engaging in the physical world, back into the game world. And so they have something called the Miiverse, which gives you a kind of avatar which you can play in video games. And they also have something called Street Pass Relay, which allows you, when you're walking around, if you choose to exchange tokens and information and Pokemon and those sort of things with people that you just encounter in the everyday space. And then when you get home, you can see what Pokemon you've collected, literally out in the wild as you've been crossing people in the street, hence the name. And then they build that social experience right inside the game. And when you do that, and when you're delivering it at the scale that Nintendo needs to deliver it at, there's basically three things which are critically important. The first is low latency. So irrespective of where you are, you want as low a latency as possible within those games. You want high availability because your game is based around it. If the availability isn't there, the game's not going to operate. You want to be able to analyze all of the data inside there to be able to make your games better perpetually. And so what I thought I'd do is share the architecture of how Nintendo went about architecting this. So on the front end, Nintendo use a service called Route 53. And this has a great feature called latency-based routing. Or routing, if you're from England. So latency-based routing allows you to direct your query at the physical infrastructure in the AWS platform, which is closest by network latency. So not physical geographic location based on IP or anything like that, but based on the continually changing environments of the internet, will route your packet to the lowest latency region every single time. And they run that across Japan, US, and Europe. And both in US and Europe, they've got a clone, an exact copy of the architecture I'm going to show you from Japan. Inside that, they have a virtual private cloud running alongside S3, and they use CloudFront, which is a content distribution network. And inside that VPC, they have a load balancer, which distributes the load across multiple, what we call availability zones. These are physically separate regions of data, groups of data centers, which have redundant capacity, redundant connectivity, and redundant power and all the rest of it. So they use a load balancer to distribute the load to increase the availability of this service as much as possible. Then they've got latency-based routing to keep the response as low latency as possible. The other nice feature they've got inside this is they're using something we call elastic network interfaces to attach to all the physical instances. This basically virtualizes your network instance away from your physical server instance. And that means if something happens to the app server on your physical instance, you can shut it down and reconnect it to your network instance, and the application just keeps on trucking. And that allows you to build out pretty sophisticated public-private subnets and VPNs which run entirely inside your VPC. And they use that for as a control plane, but also to distribute data inside the regions before replicating it globally. In addition to that, they're also using Amazon Redshift, our data warehousing service, to analyze all of this data. So they basically do a load into Redshift, run their analytics, and they can see how and where people are using this service. So it's a real production environment. I also wanted to talk about genomics. Something of a passion of mine. I worked on the Human Genome Project before I joined Amazon. And so I thought, by way of introduction, I would share my genome with you. So as you can probably tell, I have fast twitch muscles when I did my sequencing, which makes me more likely to be a sprinter. Chromosome 11, single SNP. I also have a typical normal risk of male pattern baldness, living on my X chromosome. Thanks, Dad. I am I'm genetically immune to the norovirus, which is very, very handy. And my personal favorite, a single base point mutation on my genome means that it's more likely that I will drink a quarter of a cup of coffee more than the average, which seems pretty low by my estimation, but there you go. So from either my mum or my dad, I got that one base pair. If I got one from my mum and my dad, I would drink half a cup of coffee more than the average. It's amazing what your genome can show you. This is the machine which sequenced my genome. The post-it note on the PC is a username and password. Don't do that. And if you open the little grey drawer, you can see that there's a glass slide that you put your DNA on. You shine a laser at it. It fluoresces at different wavelengths, and you can figure out the sequence. Now, this is all very, very interesting, but what these instruments allow you to do is they allow you to sequence not just a species genome, as we did with the human genome and the gorilla and the duck-billed platypus and all these other species. They allow you to sequence individual genomes. And this is very important because you can now move on from comparing species to comparing individuals within that species. The challenge, the flip side of the coin, the cost for all this is that the amount of data being generated is pretty enormous. And the cost of sequencing continues to fall. And so if you just look at it from an economics perspective, the economics are now favorable that as the cost continues to fall, more and more sequencing is going to get done. And the cutoff line is about $1,000 a genome, where genomics moves from being a purely biological discipline, a computational discipline, into being a clinical discipline. Because that's the cutoff at which you can start introducing, from a cost perspective, it's valuable to introduce genomics into the clinical setting. And we have a customer up and running on AWS today who has a platform for producing this $1,000 genome. This is what it looks like. This is an Illumina HiSeq machine. They're about the size of the lectern over there. They run continually. They spew out a bunch of data. And these things, if you ever want to talk about real connected devices and real networks producing real data, these machines deployed today are pre-configured to stream their data up to AWS. So every time you run a sample through one of these machines, it's uploading that data, if you wanted to, up onto AWS. And once it's there, the manufacturer of this company, once known for building fantastic instruments, now known for building fantastic instruments and services on top of those instruments, allow you to take advantage of a wealth of collaboration tools so you can share genomes as easily as you can share files in Dropbox, and a whole bunch of tools which allow you to analyze and assemble and work with the instruments. And they even have a marketplace where anybody can take their mechanism, their assembler, their genetic analyst algorithm, and plug it into the data that's up there and make it available to anybody else. And just to give you a sense of where this is heading, they sell a 10-pack. So you can buy tens of these instruments at a time, and we see customers buying tens of the 10-pack at a time and putting them into hospitals today. So this is the direction that genomic sequence is going, driven by this dramatic reduction in cost, and all of them pre-configured to upload to AWS. So on a related note, as genomics moves closer to the clinical world, I also wanted to touch on some work by a large pharma company called Bristol Myers Squibb. They're one of the top 5 pharma companies in the world, and they had some significant business drivers. Their question was very, very simple. They just wanted to know, how can we more effectively run our clinical trials? Clinical trials are very expensive, and they have a large amount of patient impact. But they had all these business drivers that they wanted to kind of try and address by using cloud computing. So they saw that they were spending more on server provisioning for their R&D apps, and they wanted to reduce the cost of that as much as possible. They wanted to extend the capacity of their internal environments. They already had a lot of capacity for working with these things. They were deliberately trying to slow internally hosted compute infrastructure. They realized more and more, just like we see from other customers, that they didn't want to be a data center management company. They wanted to be a drug discovery company. So they wanted to deliberately slow the infrastructure that they were managing. They had a whole bunch of requirements around onboarding security. Obviously, this is very sensitive information. They wanted to be able to validate the service and meet their compliance guidelines. And the way they did that is interesting, which I'll talk about in a minute. They wanted to do all of this whilst reducing their cost and extending their capabilities. So they didn't want much. What they went ahead and did was they ran their clinical trial simulations up on AWS. And this is a comparison. So you can see that the simulation time took around the same time. They had access to considerably more compute. We're not talking about a cycle computing mega run here. The truth is that the majority of high-performance workloads like this live in about the 256, 512 core, server environment. And they had a runtime there which is dramatically faster. So from 60 hours down to 1.2 hours to run one of these clinical trial simulations. And what that meant was that they could run more of them. And so that's what they went off and did. And the more simulations you run, the more accurate they're likely to be. And you can see the cost there. They were unable to calculate their internal costs. It was so complicated to try and figure it out that they were unable to do it. But they got a very precise number back from AWS. Now, what's really interesting is the impact that this had on the clinical trials. So you can see that this is actually for a pediatric controlled study. So the number of subjects decreases dramatically from 60 down to 40. So this is fewer children that are in hospital whilst we're running these simulations, just because of the amount of capacity available. The number of clinical interventions, in this case bloodletting, reduced from 12 down to 5. And the length of stay in hospital for each one of these children reduced from 72 hours down to 26 hours. Now, yes, the cost is less, and the amount of time it took to develop the clinical study is lower. But the real impact here is that the patient impact, just because of additional requirements and additional capacity in the compute infrastructure, was significantly reduced. So I've touched on a couple of things today, but the truth is that we see utility of the AWS platform in pretty much every direction that we look, whether it's mobile development or NASA JPL running their Mars Explorer on AWS, whether it's Airbnb in the hospitality space, a whole bunch of connected devices in the guise of Illumina and GE. We see usage pretty much everywhere, including a free steak campaign, which is my personal favorite. The question you might ask is, like, how do we decide where to focus? we see a lot of very, very early stage startups. Up there, it's a new wearable that's being developed in Australia. Attempts to improve your tennis swing. It has motion sensors in it, and it'll tell you how to improve your tennis swing. Early stage startup, they're kickstarting right now. All the way through to these very, very large companies that build gas turbines, like GE, these billion-dollar multinational companies. How do we decide where to focus our efforts? These seem like very, very different types of companies with very, very different types of requirements. But the truth is that the number one reason for adopting AWS today remains agility. Every single time we talk to a customer, yes, there's a bunch of technology that we deploy. Yes, there's a whole bunch of cost savings that they can take advantage of. But the real benefit, the thing that keeps them coming back for more, is the ability to innovate more quickly, to iterate on their products, and to use data in order to be able to drive that. So when we started AWS, we thought that early stage startups were going to be our kind of sweet spot. The low-cost, on-demand nature of provisioning infrastructure just seemed too perfect not to be adopted by startups. And we've seen a lot of success in that space, everyone from Airbnb all the way through to new wearable devices. But the truth is that those exact same benefits resonates with the billion-dollar multinational companies in exactly the same way, because it drives agility. The low cost of failure, the ability to be able to get the resources that they need is exactly the same reason that drives agility. And a lot of customers ask us, what's next for AWS? What are you going to focus on? How do you decide where and when you're going to invest and deploy your resources, your engineering resources? And the truth is that we tend to look for things that aren't going to change over time. We want to find the areas of our business which we can invest energy into today, which are going to have the longest term benefit for our customers. And we call these flywheels. These are an opportunity to invest kinetic energy today, which will keep spinning and spinning and providing value and output energy for our customers over the longest period of time. And really it comes down to the five vectors which we believe kind of underpin this agility. The relentless focus on security, enabling customers like Cycle to achieve the scale they want to be able to achieve, enabling customers to get the performance with that scale whilst delivering that in a reliable way and keeping the costs down. So every time we make an investment, it's typically in one of these five areas, and we're going to keep doing that because we believe that's the biggest value and the longest term value that we can provide to our customers. So I just wanted to round out just quickly in the last few minutes on some of the patterns of adoption that we've seen inside large enterprise customers. How are enterprise customers that want to take advantage of this agility using AWS today? So how are they thinking about it, and what are the typical use cases? And there's just a handful of them, really. As with all new technologies, the earliest workloads to start moving are the dev and test environments. And we see this with Lionsgate, well known for media production and film production. They're running their SharePoint and their SAP deployments up on AWS today. The Tokyo Stock Exchange running their dev test Oracle environments, moving more and more into a production environment. And Galata Chemicals also running their SAP environments in development as we speak, and achieving significant cost savings as they go along. So these are the early landmark beachheads, I guess I would say, for customers when they start adopting cloud computing. What quickly follows isn't just development and test, but it's the adoption of AWS for entirely new workloads. And this can be entirely new areas of business for some of our companies like Qantas, who moved beyond just operating their airline. They wanted to get into hotel booking at the same time. And they're able to spin that up. It's been a very successful business for them. PBS, media streaming and delivery to various different devices, all the way through to GE. Who wanted to build an environment where their engineers and their material scientists and their modelers could collaborate on AWS, but inside an ITAR-compliant environment. And they're able to build all of that inside AWS. And Samsung just launched their new mobile music discovery app on AWS as well. So new workloads quickly follow enterprise dev test. Then what we see are basically two flavors of supplementing AWS with existing internal resources. So this typically happens when customers want to supplement their existing web applications with the cloud. As the cloud's evolving, or if those applications were built around the time that AWS was launching, as is the case with NASDAQ, who run their market replay service up on AWS. So every time, a couple of times a day, they're able to read in all the market information and trades, and then make that available as a service to other people to replay and analyze. Sunplower, they're an equipment leasing and energy company. They run a lot of their DR environments up on AWS, again, supplementing existing workflows. And Nokia, well-known and have a very, very large mobile business, they use Redshift alongside their existing infrastructure to run all their data warehousing workloads. So that's supplementing existing workloads with the cloud. But there's also customers who do it the other way around. They want to supplement existing workloads with on-premise infrastructure. Samsung and their Smart Hub TV is a really good example of this. They have AWS serve up all the application content and all the data which flows to the device. But as soon as a customer wants to buy something and want to make a purchase, that goes back to the Samsung data centers for all the actual payment processing. So using the two together is a relatively common environment these days, and it's a step on the path to using AWS in its entirety. We see a lot of customers migrating existing applications. This is kind of the next step typically. So a good example would be Unilever, which moved about 500 of their web properties in 5 months up onto AWS. And today have over 1,700 web properties, and they can deploy a new one in just a couple of days versus 2 weeks for their previous infrastructure. And we already talked about Bristol-Myers Squibb. And then we see an increasing number of large enterprises going all in on AWS. Netflix famously going all in. You have a great quote, we have to be great at a number of things, but operating data center is not one of those things. And we work closely with these guys. They've moved virtually all of their workloads from existing infrastructure up onto AWS to power their business and allow the delivery of their digital products. Kapinski over in Germany, again, a common thread. We are a hospitality management company, not an IT services company. They want to focus back on their customers, which is one of the big advantages to agility. And Infor, back in March, announced that they were going to go ahead and move all of their infrastructure for their cloud suite up onto AWS. And Chuck Phillips, who I think is talking here tomorrow, had a great quote back in March. He said, "Friends don't let friends build data centers." So if you want to learn more about Infor and their cloud suite, nice blend of what they call micro-vertical business apps, so highly specialized apps. Conveniently, the booth is exactly outside this door. So in summary, we talked about how data drives innovation when combined with utility computing. We talked about how broad and deep services enable new businesses, so moving just beyond those principal components of compute and storage, and how valuable it is to have things like data warehousing and latency-based routing and all these things. How agility remains the #1 reason for adopting the AWS cloud today. How enterprises lead with their dev and test and with their new workloads that they want to augment their businesses with. How migration and supplementation quickly follow. And increasingly, we're seeing those enterprises go all in. So I hope that was useful. And I'd like to thank you very much for your attention. Thank you.